All right, it is 11. The roll sheet is floating about, as is a table that I created for you guys. For those of you who are not physically attending class, if you go to class meeting number 8, the table of parallel and series RLC circuit responses are there. I will be referring to them throughout probably the next 5 or 6 lectures, so make sure you get a copy of this. This sheet, exactly as it is, will also be provided to all of you for exam 1. To me, it makes sense to use the copy that you have printed out, put the equations that you want to write on one side of it, and then just keep this guy as is on the other side, and you've got yourself an equation sheet for exam 1. So, with that in mind, let's get talking about transient analysis of parallel RLC circuits. And I do not want to switch to tablet mode. All right. So let's say that we have a circuit that looks like this. We have some current source. I'm just going to call this guy IS. I'm going to call this guy RS. And then I have a resistor, an inductor, and a capacitor, all connected in parallel like so. I did remember to unmute myself, okay? And at t is equal to 0, our switch opens. So I would argue, hopefully successfully, that at the time t is less than 0 minus, when that switch was closed, our inductor had some amount of stored energy because there was a current of IS flowing through it. And hopefully we can all recall that the amount of energy stored by an inductor is 1/2 Li squared. So if I is non-zero, there's energy stored in the inductor. When that switch opens, that inductor will transfer its energy to the resistor and the capacitor, okay? And energy will just kind of get passed around until all of the stored energy at t is equal to 0 is converted to heat by the resistor. So what we're going to spend today doing is figuring out exactly what our voltage and current signals in this system look like as the energy decays or is fully converted to heat and all of our voltage and current signals decay to a value of 0. So I am going to define a few currents here. I'm going to call this guy IR of t. The current flowing down through my inductor will be IL of t, and the current flowing down through my capacitor will be IC of t. And because the resistor, inductor, and capacitor are all connected in parallel, they share a common voltage, which I will just call V of t, with the understanding that V of t in this case is the capacitor voltage, so it cannot change abruptly, right? So if it has some specific value at t is equal to 0 minus, it must continue to have that same value at t is equal to 0 plus. The exact same constraints are on the inductor current. Whatever value it has at t is equal to 0 minus, it must also have at t is equal to 0 plus. So during the transient condition, meaning the period of time immediately after which has opened, if we write a Kirchhoff's current law equation at our top node of our parallel RLC network, we get IR of t plus IL of t plus IC of t is equal to 0. And we can actually relate all three of these current quantities to that shared voltage V of t, right? So for our resistor current, that's just a simple Ohm's law relationship. We're going to have 1 over R times V of t. For our inductor, we're going to have 1 over L integral from T naught to T of V of X dx, where X is just a dummy variable for time, plus some initial condition on our current. Capacitor current is going to look like C dV by dt, and this is all equal to 0. This is what's known as an integral differential equation because it is based on the integral and the derivative of some function, right? Integral differential equations are annoying. And so we are not going to deal with them. We're going to cop out by doing a pretty simple operation here. If I take the derivative of both sides of this equation with respect to time, I change my integral differential equation into a second order homogeneous differential equation, which is pretty trivial to solve. Now, I know that not all of you guys have had Math 245 yet, so you may not agree that they're pretty easy to solve, but we can use some past experience with how circuits behave to kind of get to the same place. So if I take the derivative with respect to time of both sides, and I'm going to change things around in their order a little bit, I would get C times the second derivative of my voltage plus 1 over R times the first derivative of my voltage plus 1 over L times my voltage is equal to 0. So differentiating also got rid of this constant term, my initial condition on my inductor current. I'm going to do one more step here, and I'm going to just divide everything by C. And so that is going to leave me with the second derivative of my voltage with respect to time plus 1 over RC times the first derivative of my voltage with respect to time plus 1 over LC times the derivative, or excuse me, not the derivative, just times my voltage as a function of time is equal to 0. So this is a nice and neat second order differential equation. Again, I understand that not all of you have had Math 245, so the solution to such an equation might not be intuitively obvious. That being said, in circuits 1, we dealt with first order differential, homogeneous differential equations, and we observed that a good guess value for our voltage in an RC circuit was something of the form V of t was AE to the ST. And we're going to use this exact same guess value here and see what falls out. So if I substitute in AE to the ST into my second order differential equation, so when I take the second derivative of that, what am I going to have? So what happens when I take the second derivative of what happens when I take the first derivative of an exponential function? Let's start there. I'll pull out an s. So when I take the second derivative, what's going to happen? I pull out another s. So it's just s squared. No. A e to the st plus 1 over RC times S A e to the st plus 1 over LC times A e to the st is equal to 0. And now I'm going to group like terms. So I will have A multiplied by S squared plus 1 over RC times S plus 1 over LC e to the st is equal to 0. Right? Anything weird about my algebra or anything like that up to this point? All right, so I want the left-hand side of this guy to be equal to the right-hand side, which is 0. That can happen in a couple of ways. The first of which is if A is 0, which means everything is 0. That would be representative of if we had never had any stored energy in our system to begin with, we should expect to see that everything is always 0. So until we either charge our capacitor or pass some current through our inductor, stands to reason that all of our voltage and current quantities in our circuit should be 0. So that, while that is a particular solution to the system, it is not the general solution. Our term on the right-hand side, e to the st, will approach 0 when s is negative, but it will never be exactly equal to 0. So we're going to ignore that guy as well. So what we're going to be working with is this guy here in the middle, which I'm going to call our characteristic equation. Okay. What kind of equation is this characteristic equation? Let's start there. Pardon? Quadratic. Absolutely correct. It is a simple second order polynomial that are known as a quadratic, meaning that we can solve for the s values that satisfy the left-hand side has to equal 0 by just using our good old, I don't know, 8th grade math quadratic equation formula, right? So this guy is going to go to 0 when, let's call it S1, comma 2 is equal to negative B, so that's negative 1 over RC plus or minus the square root of B squared. So I'm going to do 1 over RC quantity squared minus 4 times A, which in this case is 1. So 4 times A times C, where C is 1 over LC, all divided by 2A, right? So what I'm going to do right now is I'm going to move this 2 from this denominator into my numerator, okay? And what that is going to do is give me S1 is equal to negative 1 over twice RC plus the square root of 1 over twice RC squared minus 1 over the square root of LC squared, where I'm just simply doing that square root bit arbitrarily, but we'll see why in a moment. And S2 is negative 1 over 2 RC minus 1 over 2 RC squared minus 1 over the square root of LC quantity squared, like so. I'm going to define two new quantities now that have specific meaning to RLC circuits, all right? The first of which is alpha. I'm going to define alpha to be for a parallel RLC circuit 1 over 2 RC. Okay. Alpha is what's known as the Neper frequency. And the Neper frequency represents the rate at which our signals attenuate, or how quickly they decay. All right? It's similar to the time constant that we observed in RL and RC circuits, but not exactly the same. That's why I'm saying similar. And it has units of Nepers per second, where a Neper is a dimensionless quantity that's representing attenuation. I'm going to define another parameter, not as the square root of 1 over LC. This is what's called the resonance frequency of our RLC circuit. Now, this is something that we are going to use, or not we, but also you guys are going to use for a very, very long time in an awful lot of your electrical engineering courses, okay? How many of you guys have ever heard of the Tacoma Narrows Bridge disaster? So that was something that happened in, I think it was the 40s or 50s or something like that, where they had this long suspension bridge and the wind started blowing at the same rate as the resonant frequency of the bridge, causing it to oscillate. And because it was at its resonant frequency, every oscillation caused the amplitude to get larger and larger and larger. It seemed like a positive feedback system. The wind was so strong and the vibrations were so large that the bridge tore itself apart. That is a representation of what the resonant frequency is. It's where you can put the smallest amount of energy into the system and get the absolute largest amount of response, okay? So if you've ever seen people at a construction site loading up a scaffolding, you might see them hit the structure with a wrench every now and then. What they're doing is literally listening to the resonant frequency of the system, because as that pitch gets lower and lower and lower, that means that that thing is more and more likely to fail, because the resonant frequency is getting closer and closer to a DC state where literally existing will cause it to fall apart. Okay, so this is the resonant frequency again, and it has units of radians per second. So it is representative of the oscillations that we are going to see when we look at these transient analysis conditions. So if I substitute in alpha and omega naught into my equations for S1 and S2, I get negative alpha plus the square root of alpha squared minus omega naught squared, and I get negative alpha plus, minus the square root of alpha squared minus omega naught squared, right? So these are the real definitions of S1 and S2 that we're going to wind up using. But now I would like to talk about S1 and S2 for a little, okay? S1 and S2 are what are called the eigenvalues of the system. If you've had Math 245, you will know what that means. If you haven't, it just means they're the natural frequencies of this system. So when we don't have some outside excitation function, which is exactly what we're doing when we take that source out when the switch opened up at t is equal to 0, These are telling us how our signals are going to decay. These are the natural frequencies that our system responds at. It should be fairly obvious to see that there are going to be three distinct cases, okay? So, let's look at case number one. Alpha is greater than omega naught. When alpha is greater than omega naught, we say that the system is overdamped, okay? When a system is overdamped, that means that the signals decay in a long amount of time, okay? So it's not a very efficient system. It reaches its final value slowly, okay? In this case, S1 and S2 are both negative real numbers. All right, so if we circle back around here to our guess value, AE to the ST, this is a particular solution. Due to the superposition theorem, the sum of particular solutions is also a solution, meaning that, I'm going to run out of space here, but V of t is equal to A1 e to the S1t plus A2 e to the S2t is a solution to our voltage equation when our system is overdamped. All right. And I don't have my equation sheet on me. Let's look at it real quick here. This first guy right here, the response type overdamped, alpha is greater than omega naught. We see that our response is A1 e to the S1t plus A2 e to the S2t. And then this guy comes into play when we start doing the total response, which will be next Wednesday. So everything seems hunky-dory there. Sorry, what was that? Okay. All right. Now let's look at case number two. What happens when alpha is equal to omega naught? So we call this critical damping. And this is the best case scenario, okay? When a system is critically damped, its signals, voltage and current, decay to their final value in the shortest amount of time possible without having what's called overshoot or ringing, okay? So it's gonna, from a graphical perspective, it's gonna look very similar to overdamping, except that it's just gonna get to the final value faster. So if I'll draw a picture in just a second. In this case, S1 is exactly equal to S2 is exactly equal to alpha. And so it's going to be, again, real and negative. Now, the problem that we would face is that if S1 and S2 are identical, we could combine this response equation into one thing that would just be a single coefficient A times e to the ST. But that does not do a good job of realizing that there are two initial conditions on our system because there are two energy storage elements, okay? So without any derivation, because that's well beyond the scope of this class, it's something that you'll learn in Math 245 and ELEN 321. Whenever we have a critically damped system, we have to introduce another term in order to account for both of the initial conditions on the system. So we would see for a critically damped system that our voltage will be of the form A1T e to the alpha t plus A2 e to the alpha t. And actually, this should be negative alphas here. So this is what allows us to have two initial conditions being influencing the response of our system. So we're going to do case 3 right here, and then I'm going to draw a picture real quick. So for our system that I drew earlier, where we knew that the current at t is equal to 0 had some non-zero value, or the inductor current at t is equal to 0 had some non-zero value, the overdamped response would look something like this. So it's just really a simple exponential decay. In comparison, our critically damped response would look something like this. So it just looks very similar. It's an exponential decay, but it hits its final value of 0, or very close to 0, significantly more quickly than the overdamped case. Our last condition is that alpha is less than omega naught. And we call this type of system underdamped. So let me scroll up real quick and let's look at our equations for S1 and S2. So if alpha is less than omega, what happens to S1 and S2? Specifically, what's happening underneath this radical sign in both cases? It's going to be negative. So we're going to have some fixed portion that is a real number plus some imaginary portion as well. And the imaginary portion is going to be plus whatever that imaginary portion is for S1 and minus that same imaginary portion for S2. So we can say that S1 and S2 are complex conjugates of each other, okay? So the natural frequencies are complex numbers where S1 is equal to the complex conjugate of S2. What that translates to is oscillations, okay? So most of you have ridden in a car before, right? I would assume at this point you're all somewhere close to 20. That technology has been around for over 100 years, so cars should be fairly straightforward. How many of you have ever hit a bump? Probably pretty often because the roads in Louisiana are terrible. That's why we have the worst or the highest auto insurance rates in the country, or damn near. So the spring systems in your cars, as they deteriorate, actually begin to look like underdamped systems, meaning that you don't get a smooth transition. Instead, it jiggles for a while, right? That is what an underdamped system looks like. Mathematically, I didn't give myself enough room here. V of t will be of the form B1 cosine omega dt plus B2 sine omega dt, and this whole thing is multiplied by e to the minus alpha t. okay? So we have some sort of sinusoidal oscillations where omega d is defined to be the square root of omega naught squared minus alpha squared. This is what's called the natural frequency of oscillations. So what this would look like, I use a red color for this, is we're going to see that in an overdamped system, we're going to hit 0 really quickly. We're going to overshoot it. It's going to come back around. And we're going to oscillate. And the envelope of the oscillations is e to the minus alpha t. So it's still, we're just going to see sinusoidal oscillations that are gradually decaying towards a 0 value. Okay. So this is critically damped, overdamped, critically damped, and underdamped, where they all come from, and the reasons why we have to have 3 different responses to solve that one single second order differential equation. It's because there are 3 different conditions on the relationships between alpha and omega naught. So now let's visit our table again real quick here, okay? So in this table, I give you the response equation, or actually, so over here on the left-hand side, we have response type. If alpha is greater than omega naught, it tells us that we have an overdamped system. So we have a mathematical equation for alpha, a mathematical equation for omega naught. We have a response equation. We have the first derivative of our response equation. That's incredibly important. And then we have the definition for our parameters. So for an overdamped, I give you the equation for S1 and S2. When we get to a critically damped system, notice it says alpha is equal to omega naught. We have our response equation, and then again, we're going to have our first derivative equation. There's no new parameters that we need to worry about since everything is just based off of alpha. We know how to calculate that. So no big deal. And then when we get into an underdamped situation where alpha is less than omega naught, I give you the response equation, the first derivative, and then the definition for omega d. So everything that we have talked about to this point, other than the why we have these response equations, is included in this table. Okay, so all that is there. So let's talk about why you're going to have to pay so much attention to these derivative relationships. Okay, so in our system, we have 2 energy storage elements. It's either going to be a capacitor or an inductor. And therefore, we have 2 calculus-based relationships, right? We can either express the voltage drop over the inductor as a function of the current flowing through the inductor, or vice versa, and the exact same thing for the capacitor. So we're going to use these 2 equations to look at the 2 different initial conditions on our element of interest, meaning one is going to be representative of the current and the other one is going to be representative of the voltage. And there's always going to be a derivative-based relationship between those 2 quantities for our energy storage elements. I know I said a whole hell of a lot of words there. So let's actually just work out an example problem or 2 and put this into practice. So oh no, I'm just going to make something up. So the numbers might be awesome or they might be terrifying. We'll find out. All right. And I didn't bring a calculator. Yes, I did. I brought my thing here. Okay. So let's say that we have the following circuit. I got to make sure it's going to work the way I want it to first. Yeah, this will work. All right, so this is my circuit of interest. So the first thing that we're going to want to do, we're going to want to make sure, since we only know how to deal with parallel RLC circuits to this point, is that this is going to behave like a parallel RLC circuit. And so I would argue that when that switch closes, we will see that all of the current that is being supplied by that 5-volt source is just going to flow through that 8-ohm resistor, and it's going to circulate in that little loop. The 5-volt source will no longer be connected to the 10-ohm resistor, the 2 Henry inductor, or the 1/2 of a farad capacitor. And so we are left with just a simple parallel RLC circuit. Anybody disagree with that sentiment? Start there. All right. So our first step is always going to be to calculate alpha and omega naught and determine whether we have an overdamped system, a critically damped system, or an underdamped system. Because if we don't do that, we're just pissing in the wind. We have no idea what direction to head, okay? So let's just write that down. Step 1, calculate alpha and omega naught. By the way, your homework problems, literally, there's 5 parts to every single one of them that are the 5 steps in the correct order to do them. So you will get significant practice of doing these problems in the exact order I want you to do, because I have set it up to force you to do that. Comply or obey or whatever. All right, so we need to calculate alpha and omega naught. Alpha is 1 over twice RC. Let me get my calculator out here. So that is going to be 1 over 2. What value should we be using? Let's start there. Is it going to be 10? Is it going to be 8? Is it going to be a parallel combination of 10 and 8? Is it going to be the series combination of 10 and 8? It's just going to be the 10. Okay. And then we have the 1/2 of a farad. So this is going to be alpha is 1 over 10 is 0.1 neppers per second. Making sure. Yeah, 1 over 2 RC. All right, that's easy enough. Omega naught is the square root of 1 over LC. So that is going to be L, which is 2 Henries, times C, which is 1/2 of a farad. I'm going to raise that to the minus 1/2 power. So that's me taking the square root of the reciprocal. So the square root of the reciprocal of 1 is 1, right? So our resonant frequency is 1 radian per second. Since alpha is less than omega naught, what kind of system do we have? Underdamped, all right? All right. Step 2 is we are going to analyze our circuit at T is equal to 0 minus. We're really only going to be looking at a couple of different things. So let's go ahead and define what those various things are, okay? I can call this guy IR of T. I can call this guy IL of T. And let's call this guy IC of T. Let's call this voltage V of T. Really, what we need to pay attention to depends on what our quantity of interest is. So in this case, I'm going to be real general. And I'm going to look at, let's try to find my inductor current and my capacitor current, okay? So we're going to try to find those two different quantities. So let's be explicit here. Find IL of t and IC of t. And so because I'm trying to find something related to my inductor, I'm going to need to keep track of my inductor current and my inductor voltage. Because I'm trying to find something related to my capacitor, I'm going to have to keep track of my capacitor current and my capacitor voltage, remembering that the inductor voltage and the capacitor voltage are the exact same thing. So effectively, I don't need to pay attention to what's going on with the resistor. As it turns out, I will never have to pay attention to what's going on with the resistor. Because the resistor does not have a derivative-based relationship between the resistance and current, we can never actually use it to determine anything. We will always find the capacitor quantity or inductor quantity first and use that to find the resistor quantity, which in this case, if I knew IL and IC, I could use KVL and find IR. Or if I knew the voltage, I could use Ohm's law and find IR. And the voltage is the same as the voltage drop over the resistor, so, you know, blah, blah, blah. So you'll never actually bother keeping track of the resistor stuff unless I specifically tell you to, because I got in a weird mood when I assigned the problem or something like that. So with that in mind, let's look at this circuit at t is equal to 0 minus. So we have a 5 volt there, an 8 ohm resistor there, I believe. An 10 ohm resistor here. My inductor is going to look like a short circuit. My capacitor is going to look like an open circuit. So here is V at 0 minus. This guy is IC at 0 minus. And this guy is IL at 0 minus. And again, really don't care about what's going on with the resistor. So we're not going to bother keeping track of it. It's just a waste of time. So who can tell me what the value of any of these three quantities are? This is a particularly difficult circuit to analyze at your current level of electrical engineering expertise, right? It should take a thorough analysis, maybe even mesh, because there's one whole loop in there. IC is 0. All right, let's start with something real easy. IC is 0 because it has to be. It represents the current flowing through an open circuit. I can't write to save my life today. All right. So there's another piece of low-hanging fruit here, as it were, as well. What does the voltage drop over the capacitor have to be? No. So what's the voltage drop over the inductor? Let's start there. What's the voltage drop over the inductor? It's 0, because the inductor is being represented by its DC equivalent, which is a short circuit. Since the capacitor is in parallel with the inductor, they have to have the exact same voltage. So if the voltage drop over the inductor is 0, the voltage drop over the capacitor is also 0. So V at 0 minus is 0 volts. So our last quantity of interest is our inductor current IL at 0 minus. What's that going to be? 5 over 18, yeah. 5 volts divided by the total series resistance seen by the source. So 5 over 18 amps. Fractions are good enough for me. All right. This is really the level of complexity of circuits that you're going to have to be analyzing when we're looking at things at t is equal to 0 minus and t is equal to 0 plus for the most part. I might be a jerk and occasionally throw in a dependent source every now and then. It's not going to be the end of the world. You would just use the test source method or whatever you choose to do to find the equivalent resistance and then use that to calculate alpha, omega, naught, and you can actually just substitute that equivalent resistance in and work from there. Did not mean to throw my pen at the ceiling. All right, so step 3, what do you think it is? Exactly right. So at t is equal to 0 plus, I'm not going to bother redrawing the 5-volt source or the 8-ohm resistor because they are not influencing the behavior of the capacitor and inductor in any way, shape, or form. So our resistor is going to continue looking like a resistor because it is nice and well behaved. Our inductor, I'm going to replace with a current source, which is going to have the same direction as my inductor current and the same magnitude as my inductor current at t is equal to 0 minus, because the current flowing through an inductor cannot change abruptly. The voltage drop over a capacitor cannot change abruptly. So what should I replace that with in this particular example? A short circuit, because V was 0, so I need to force a 0-volt drop, which is a short circuit. So here is IC at 0 plus. That is literally the only quantity that's going to change. So IC at 0 plus is going to be something. We know that V at 0 plus has to continue to be 0 volts, and IL at 0 plus has to continue to be 5/18 of an amp. So another very tricky circuit to analyze. What is IC at 0 plus going to be? Incorrect. Negative 5/18, right? Because all of the current here is going to flow up in the opposite direction as we have defined IC. All right, the circuit analysis portion is complete. Now, this is where things will arguably be new. All right, so step 4, and we have 2 possible step 4s here because we have 2 quantities of interest. And so I'm going to look at the capacitor voltage. Now, it's going to seem weird, okay? Because the capacitor voltage is not one of the 2 quantities that I'm interested in. I'm doing it purely, if I want to find IC of t, I'm going to have to look at V of t, right? Because IC of t is the derivative multiplied by the capacitance of the voltage, right? So in order to get IC of t, I'm going to need to know V of t. So step 4, in this case, will just be use response equations, all right? So we know that V of t, because this is a underdamped system, right, will be of the form B1 cosine omega dt plus B2 sine. Oh, I need to save this and close it out or it's going to keep giving me that stupid error. Where is my... There we go. Omega dt e to the minus alpha t. So before we move along, it stands to reason that might be a good idea to calculate omega d, right? We're going to have to use that at some point or another. So as a quick aside, omega d is going to be the square root of omega naught squared, so 1 squared minus 0.1 squared, .99, I'm going to call it 0.995. There are some other stuff, but it's like 4.99 something, so 0.995 is good enough for me. This guy has units of radians per second. All right. So here's where things get arguably interesting. At t is equal to 0 plus, what does this big ugly equation reduce to? So let's start by looking at the e to the minus alpha bit, okay? So if t is equal to 0, e to the 0 is what? 1. So this term right here just goes to 1. What is the sign of 0? 0. So this whole bit goes away. What is the cosine of 0? 1. So we have v at 0 plus is equal to b1 is equal to 0 volts. We already know one of our two coefficients. I'll be damned. It's fantastic. All right. We're making quick headway here. Now we're going to have to use our derivative-based relationship, right? So IC of t is C dV by dt. And this is where the table is wonderful. Because, while I close that out, let me open it. In this case, we're simply substituting v for y, right? So I already gave you the derivative. You don't ever have to calculate it yourself. That is the beauty of the table. So omega d b2 minus alpha b1. So C omega d b2 minus alpha b1 cosine omega dt. I think it's minus, but let me double check. Yep. Omega d b1 plus alpha b2 sine omega dt e to the minus alpha t. If I copied things down from the table correctly, which you guys can tell me if I screwed that up or not, but I think I got it. So what does this guy reduce to when t is equal to 0 plus? E to the minus alpha t is again going to be 1. This whole term right here is going to go to 0 since sine of 0 is 0. So we're going to be left with c times omega d b2 minus alpha b1. Very important to remember that c. That is a common mistake that I see students make. And this is going to be equal to negative 5/18 of an amp. So since B1 is 0, we have C omega D B2 is equal to -5/18, which means B2 is -5/18 times 1/c omega d, right? So let's just throw that into the calculator here, -5/18 times 1/0.994987437 times c was 1/2, 0.5. B2 comes out to be -0.558. What should the units of B2 be? Anybody got any ideas? Volts. Yeah, we could do dimensional analysis and it would totally work out right. But if the unit on B1 is volts, the unit on B2 needs to be volts as well because we're adding these two quantities together. That's easy enough. All right. So we now have enough information to calculate V of t and IC of t, right? So V of t is going to be fairly straightforward, even though we're potentially not going to use it. V of t is just B1, which is 0 times cosine blah, 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 plus B2, so that would be -0.558 sine 0.995 t e to the minus alpha, which was 0.1 t volts. IC of t, we're going to have a new coefficient. It's going to be the exact same form, B1 cosine omega dt plus B2 sine omega dt, blah, blah, blah. It's just our new coefficient is just going to be C times omega d B2 minus alpha B1. And we know all of those quantities. And our coefficient for our sine term is going to be C times negative omega d B1 plus alpha B2. So all that's trivial as well. So if I plug in my numbers, let's see, C is 0.5 times omega d, I'm going to save that, that'll be easier. Sorry, 1/2 multiplied by omega d, which is x, minus this guy, minus alpha b1, where b1 is 0, so that doesn't do anything. 0.479 cosine 0.995 t plus, for now, 1/2 multiplied by omega d b1, so that none of that does anything for me because that's 0. So it's just going to be negative alpha, so negative 0.1 times B2. So plus 0.027 0.28, sorry, do it rounded a little bit better. Sine of 0.995 t e to the minus 0.1 t amps. And just to make sure we're doing everything correctly, 0.479. Hold on. I feel like I've made a mistake here. The reason why I feel like I've made a mistake here is that at t is equal to 0, this thing is supposed to go to -5/18. -5. Let me erase all this crap. is negative 0.277 blah, blah, blah. So it looks like it's supposed to be this term. So I made a dumb mistake somewhere. Let's figure out what that was. This happens pretty much every year, par for the course. So B1 is definitely supposed to be 0. Let's see, square root of 1 minus 0.1 squared. Let's save that as x. All right, so I have 0.5 times and I'm solving for x. Negative 0.558. All right, that is what that needs to be. Okay, so let's try this again. This part checks out, this part checks out, this part checks out. All right, so C, 1/2 times omega d, which I have stored as y, times B2, which I have stored as x. Yep, dumb calculator error. Where is my, sorry about that. So this one is negative 0.277 repeating, which is 5/18, or negative 5/18. So that all works out. Let me double check this answer here real quick. 1/2 times negative 0.1, because it's negative alpha times B2, which I have stored as x. All right, so that one was correct. 0.028. All right, so that's IC. That guy all works out. And we will verify it using MapCat. Or, yeah, MapCat, or no, LT Spice. So how can we go about determining the inductor current? Okay, let's talk about that real quick, and that'll take us to the end of class probably. We got a couple of different ways that we can do it, okay? First is the inductor current is equal to 1/L times the integral of this guy. We know this, we could do the integration for it. So Bob's your uncle, we would be able to get our answer that way. Or we could actually repeat these exact same steps where our first equation, we could put in our inductor current. So we could put in IL of T here, and our derivative-based relationship would be the voltage drop over our inductor and go that route, right? So I'm going to do it that second way, just for the sake of argument. So I'm just going to call this 4.2. IL of T is going to be B1 cosine omega dt plus B2 sine omega dt e to the minus alpha t. Where I want to be really clear here, this B1 and this B2 are not the same as what we calculated earlier. IL at 0 is going to be equal to B1, which is going to be equal to positive 5/18 of an amp, right? Because IL at 0 plus was 5/18 of an amp. Then we're going to have V of T is equal to L times di by dt, which would be L, scroll up here, omega d B2 minus alpha B1 cosine omega dt minus omega d B1 plus alpha B2 sine omega dt e to the minus alpha t. So V at 0 is going to be L times omega d B2 minus alpha B1, which must be equal to 0 because the voltage drop at t is equal to 0 plus, or t is equal to 0 minus because it's a capacitor voltage, is equal to 0, which tells me omega d B2 is equal to alpha B1. So therefore B2 is equal to alpha B1 divided by omega d. So that would be alpha 0.1 divided by omega d, which I have stored as variable y, multiplied by B1, which is 5/18, 0.0279 or 0.028 amps. And from this, IL of t is 5/18 cosine 0.995 omega d t plus 0.0279 sine 0.995 t e to the minus 0.1 t. Doing it a second time where all the steps are essentially exactly the same, kind of can do it a little bit quicker. All right, so we got 10 minutes, so I think that's enough time for me to pop out LT Spice and hopefully prove that I did this right. We shall see. Always a chance I made some sort of dumb mistake. In chat, let's see. What? Oh, okay. All right, so let's pull up LT Spice. And let's get this thing out of the way. I have a resistor, an inductor, and a capacitor all in parallel. And I'm just going to arbitrarily choose my ground to be the node here at the bottom. So this is a 10 ohm resistor, if I remember correctly. This was a 2 Henry inductor. This is a 1/2 of a farad, so 0.5. Put this up here. Cut that little stub off there. Okay. I'm going to have to put 2 initial conditions. So my first one, .IC, initial condition, the current through inductor 1, so L1, was 5/18, right? So that was 0.2777777. You got a calculator in front of you, right? 5/18 is 2.5/9. I don't know that that helps. 0.2, and then a whole bunch of sevens. Control M for a new line, our second initial condition, .IC, the voltage at node 001. I know it's going to be node 001 because it's literally the only node that isn't ground, is equal to 0, right? Because our initial condition on our capacitor voltage was 0. So I'm going to put those two guys right here. This is going to be transient analysis. So because alpha is 0.1. I'm going to let this guy go for about 1 second and we'll just see what happens. So simulate, run, stop time of 1 second. And let's look at what quantity do we want to look at? We've measured the voltage of the capacitor, the voltage of the inductor, which are the same thing, the current through the capacitor and the current through the inductor. So literally pick one of those quantities and we'll rock and roll with that. Current through the inductor. All right, my mouse was already over it, so that makes sense. All right, so 1 second isn't quite enough, so let's change this to 3 seconds. That's still not enough time. Okay, let's change it to 10 seconds. Let's see what's going on here. Still not quite enough time. All right, let's try 20 seconds. What I'm doing is I'm just trying to see it actually settle to something. So if it's still moving around a lot, still moving, dang. All right, that's good enough for me. All right, so at roughly a minute, it's going to be pretty stable, which makes a capacitor value of 1/2 farad is absolutely enormous. So that actually seems fairly reasonable. All right, so I can check my answer by adding a trace. So if I am not mistaken, my inductor current was, I need to open parentheses here, 0.27777 because it was 5/18 of an amp multiplied by the cosine of 0.995 multiplied, and here's something very, very important, okay? LT Spice interprets everything as all of its angles as degrees. We have the angular frequency, so we need to multiply by 180 degrees over pi to get LT Spice to do this correctly. So 180 divided by pi multiplied by time, and to that I'm going to add 0.028 amps multiplied by the sine of 0.995 times 180 over pi times time, close parentheses, multiply this by the exponential of negative 0.1 times time, and it matches exactly. Which means our analytical solution for our inductor current is correct because it matches our simulation literally exactly. Those two lines are 100% superimposed on top of each other using the exact same scale. Now, I will say, when you have a critically damped system, the second coefficient is going to be, or excuse me, the first coefficient is going to have units of volts per amps, volts per second or amps per second, and LT Spice doesn't know how to do that. So it would be better for a critically damped system to leave the units off. What is going to happen is you would see, so let me show you what's going on here actually. So if I delete these units of amps here, it still matches perfectly because my scales are identical. But it is possible that sometimes it will automatically change your scale on the right-hand side. And so you'll get something like this and you'll be like, well, damn, I got it wrong. But you didn't because the scales don't match, okay? So that's definitely something to be aware of. That is a very common place where I see students get extraordinarily frustrated. They swear to me up and down, they've done it correctly, and they have, They just didn't notice that having it range from 500 to negative 500 is not the same as having it range from 300 to negative 250. So the scales need to match on both sides, or else the graphs don't look like they're representing the exact same signal, even though they are. So that is definitely something to pay attention to. All right, we went to full time today, so I'm going to shut up. On Monday, when we come back from our weekend, we are going to talk about the transient response of series RLC circuits. And then next Wednesday's lecture will be the total response, where we include having sources in, and that'll probably be a very short lecture, roughly 30 minutes to 45 minutes tops, because that is the start of my Easter break, and so I'm going to try to bounce out of here as early as possible. So anyway, hope you guys have a great weekend. Your homework assignment for this has already been posted. So if you have any questions about any of this or the LT Spice stuff, feel free to send me an email or whatever.